Separation of variables. One thing that's going to come up sometimes is systems of equations. Like, for example, you could have something like x dot is equal to 5xt, y dot is equal to 2y squared, t squared, and then with boundary conditions. Okay. So when can you solve those? There are ways to solve them. I'm just going to talk about the kinds that you'll see in this class. And there are ways to solve other ones. But key in this class is whether the equations are coupled or uncoupled. In this class, we'll only have to deal with uncoupled equations. So what that means is that, so let me make that a semicolon. What an uncoupled equation means is that each dependent variable stays in its own equation. So an example of a coupled equation would be like x dot is equal to x yt, and y dot is equal to, x squared t squared. We don't have a way to solve these in this class. If they're uncoupled, they stay in their own equations. Then you just solve those as two separate differential equations. They each have their own boundary conditions. Okay, and so it's a system, but to you, it's just two differential equations problems. Separately. Okay, so let's go back to the example I showed. Now, well, are those coupled or uncoupled? Those are uncoupled. That's good. And then can we solve? Well, that means we can look at them one by one. So let's look at the first one. Is that something we can solve with separation of variables? Yeah, because you can write this as a function of x times a function of t. What about this one? Can we solve that by separation of variables? Yeah, because it's a function of y times a function of t. And so we'll do this one first, come up with an answer, and do this one and come up with an answer. Okay, so now here's where we are in the math preliminaries. That's all I want to say about separation of variables. Okay, so first was ODEs using separation of variables. Separation of variables, and we're done with that one. And now we're going on to derivatives of vectors, as long as the coordinate system is non-rotating. And then we're going on to product rule for vectors. And then chain rule for vectors. Okay, so the next one is derivatives of vectors in non-rotating coordinate systems. And all you do is take the derivative of each individual component of the vector independently. Okay, so let's say that we have a vector u that's equal to, the components are ux, uy, uz. Then to take the derivative of u, that's just the derivative of the x component, derivative of the y component, derivative of the z component. Why does it matter whether the coordinate system is rotating? This is kind of for just to put in the back of your brain for later. Well, this way of writing u, remember, means the same thing as this. So our vector u is equal to ux times I plus uy times j plus uz times k. Right? I just use a different notation, but that's what it means. And so if you take a time derivative of u, you have to use the product rule here. And it says ux dot times I plus ux times I dot plus uy dot times j plus uy times j dot plus uz dot times k plus uz times k dot. If the coordinate system, so these things, what the hell are those? You know? So if the coordinate system is non-rotating, I dot and j dot and k dot are 0. So it's no problem, those go away. But if the coordinate system's rotating, we need to come up with a way to represent those. Okay, and that's where all the mess is going to come in. That's where all the complexity comes in when you deal with rotating coordinate systems. Because the thing is, I, j, and k are changing in time, so those time derivatives are non-zero. Yeah. So for now, just remind yourself to appreciate when a coordinate system is not rotating, because it's going to get really messy. Any questions about that? Okay, so next is product rule with vectors. I guess I sort of used it here above, but remember, this is sort of the key thing with product rule with vectors. There are 3 different ways to multiply vectors. You can multiply a vector by a scalar like we did here, or you can take the dot product of 2 vectors, or you can take the cross product of 2 vectors. And so we need to think of what the product rule means in all these cases. The product rule with vectors. So first, if you multiply a vector by a scalar, so d dt of the quantity, so x is our scalar and u is our vector. Well, this is equal to, another way you can write this, by the way, people would put the xu in parentheses and then draw a line over it to show we're talking about everything inside the parentheses, and then a dot over the line. That says a total time derivative of everything inside there. But what would you guess the product rule is here? Without, this is a safe space. Okay, so it would be x dot u plus x u dot. Okay, so it works just like the product rule for scalars. The thing that's going to be an issue in one of these cases, only one of them, is that the product rule with scalars, you're multiplying scalars order doesn't matter. So this is an aside, but that's not a smiley face. This is serious. This is also equal to x dot u plus u dot x. Okay, but don't think that way. Okay, and then dot product. So say we're taking d dt of u dotted with v. What would you guess the first term is of the product rule? Wrong. So it's u dot dotted with v plus, what's the second term? Yep, u dotted with v dot. And because order doesn't matter with the dot product, that's also equal to u dot dotted with v plus v dot dotted with u. But don't think that way. And then cross product. So d dt of u crossed with v is exactly what you'd hope it would be. U dot crossed with v plus u crossed with v dot. And the whole reason that we don't want to think in that crossed out way is that this is not equal to u dot cross v plus v dot cross u, because this v dot cross u is not equal to, oh, this v dot cross u is not equal to u cross v dot, because order matters with cross product. And then the last thing is the chain rule. So the chain rule with vectors. So the way this is going to come up is, say that you're taking a derivative of a vector that's a function of a function of time. Okay, so f is a vector function. Its argument is, like, say, mostly it's going to come up for us, maybe always it'll come up for us with the g is going to be like a position, x, y, or z, but x, y, and z positions are functions of time. Okay. And this is equal to the derivative of vector f with respect to g times dg dt. So it works just like scalar chain rule, just that one of those derivatives, the df dg, is going to still be a vector. So, and then you're multiplying that vector by this scalar. Here's the way it'll come up. It'll come up in dynamics like this. So we know that acceleration is the time derivative of the velocity, right? But what if we know the velocity vector as a function of a position variable instead of the velocity vector as a function of time? Okay. I mean, acceleration is not dv dx, it's dv dt. So if this is all we know, and that would come up in any kind of energy analysis, you get your velocities as a function of position. At first glance, you would think there's nothing you can do. But if you use the chain rule, then the acceleration is equal to the time derivative, and I'll write it in that form of that I have of defining the chain rule, That's the derivative of the velocity, which is a vector, and it's a function of x. And so we can write that as dv dx times dx dt dx dt is just the x component of the velocity. And so the acceleration is dv dx times the x component of the velocity. And doing it that way, we can take the time derivative of the velocity to get the acceleration without ever knowing what velocity is as a function of time explicitly. That's going to be really useful because, acceleration is the key to putting kinematics together with forces and masses, because that's how you go through Newton's laws, is through acceleration.